Okay, yeah. Give you a few minutes to read it, think about how you would solve it, then we'll come in and then do the solutions.
Also, Dr. Denard,
Yes.
for the students that have the exam conflict on Thursday,
Uh-huh.
if we were to take the exam tomorrow, when would the take-home exam be due for us? Would it still be due Thursday for us?
Yes, everyone is do the same.
Oh, okay.
Yeah.
And then, like, if I were wanting to take the exam tomorrow, like, what time would I be able to like take the exam?
What time is in the syllabus? 5:30?
For Thursday, I believe so. Yeah.
Yes, so it would be that. Oh, Thursday, what, for tomorrow, I mean. Let me check.
I don't think the syllabus had a time on it.
Okay.
Does this also apply if we were gonna take it on the 30th as well?
Yes.
Okay, it would be the same time.
Yeah, let me check what if I had put a time. Oh yeah, did not put a time. Well, silly me. All right, well, let's okay, let's do I'm announcing this right now, so you guys will know. I'm gonna post an announcement. Yeah, exam the in-class portion is 40 points. So it's actually short. It's only yeah, two or three short problems. So you better know how to do this problem on the take home. Yeah.
When will the take home portion be released? Was that today?
It's already done.
Oh, okay. So it's in like assignments.
Yep.
Okay. Thank you.
It was 11 a.m. today. So I'm giving you guys even more time.
Okay.
Because after I designed it, I was so proud of it. I was like, it's time to release it. Release the Kraken. I was so excited. I was like, I can't wait. Let's just put it out there. At least I'll find out if there's a mistake in it pretty soon. Hopefully some of you guys already started it.
Makes sense.
Did you say that the in-class, like the in-person problem that we're doing for the exam, is that going to be, is it 40 points?
Yeah, it's 40 points, two problems, maybe three,
Okay.
but short,
Okay.
really. So I'm taking into account the fact that this take home will probably take you a couple hours, maybe more.
Right.
So then I'm taking that into account. So the in-class exam is basically should not take you more than an hour. It should not. So it's going to be short problems, things that you can quickly solve.
Also, Dr. Denard, on your announcement, you said the take-home exam is due at 3 p.m., but I think on the actual assignment it says 5:30. So which one's
Oh,
the
it
correct
does?
time?
Oh, it
Yeah,
should be 3
correct.
p.m.
Oh,
Let me
okay.
let me fix that. It should be 3 p.m. Okay, guys, spend some time looking at that problem. I'll fix those things. These are just logistical issues. Don't worry about that. And spend some time looking at that problem.
Also, Dr. Denard, what time will you have your office hours on Wednesday?
Same time, 4 p.m. Is that usually?
Okay, just wanted to make sure.
Mhm.
I just wanted to clarify. So the take-home portion is 60 points, and then the actual in-person exam is 40. Oh wow.
I know. Now, let me say this though. Well, maybe I have to make another announcement now. I'll say this. You know, you can get at the very least 47. I would say about that, even if you messed up the first part really badly. Read the exam, and then when you tomorrow we'll speak about it.
Okay.
Yeah. So it's not designed to fail you. Okay, I'll give you guys another 5 minutes, and then we can go ahead and solve it together, and I can go ahead and explain more or less how it's solved. I will give Alex a problem on PDRs and PFRs to go over with you in his office hours, as I don't think I didn't have time to find one that I really liked. So, you know, instead of giving you the one that may be on the exam. So that's always the issue, is to remove the bias. Because I already wrote the exam, so I have to remove the bias of reviewing something that I think that's exactly on the exam. It's a tough decision. Okay, so now you've read the problem. Maybe you thought about how to solve it. Maybe you haven't, and that's okay. Are we recording? Okay. So, and maybe you have, maybe you haven't. So it's telling you that you have a first order reaction that is in a packed bed reactor, and you can assume that it's isothermal. and you have spheres, porous catalyst spheres that are basically to catalyze your reaction, and you give an activation energy. And you're given this particular piece of data that at 50 degrees Celsius, there is 70% conversion in that reactor. So the first question is asking, given if the Tilly modulus is small, so Tilly modulus being small, meaning the effectiveness factor is equal to 1. So it's asking you that if the reaction temperature is increased to 60 degrees to calculate the conversion based on changes in the effectiveness factor. So the way you solve this problem, and you might be surprised, but you might not be surprised that you actually go through the same process of following your mole balance. So you can start with the mole balance for a PBR. Oh, let's change the color. So you can start from a mole balance. Oh, let me now share. Sorry, let me share my. I wonder if there's a better way to do this. Let me try something different. Let me see if that works. Yes, that does work. Okay, sorry, I'm doing a couple of changes here and there. Okay, now let's share the scribble. There we go. That's what I wanted to do. Can you guys see this?
Yep.
Okay, good. That's what I wanted to do. That works. Okay, so I'm gonna try to maybe minimize, making sure it works. Okay, good. So you can start the same way. You can look at the mole balance on a PBR, and you can write it in terms of A. So it's gonna be dFADW equals RA. Yeah, equals RA. And that's equal to minus effectiveness factor times some K prime CA. So that's your mole balance. You start from there. You can do some manipulations here, right? So you can say that, you know, FA is V times CA. So you can have V dCA dW. So you can do those manipulations we've done before. So you can keep going. So you can have then dCA dW equals this K prime over V times CA. And you can integrate from, you can separate and integrate. So you can have dCA over CA equals minus NK prime over V dW. So you can integrate here from 0 to W, integrate here from CA naught to CA, right? So now this is you know this information here. So you know this because you know what the conversion is at 50 degrees. So you can have log of CA over CA naught is equal to this. And that's equal to log of 0.3, right? So it's 70% conversion at that temperature. So that's equal to minus 1.2. Okay, so now we basically know that this quantity at 50 degrees, right? So this is the first thing you do. Again, you might be surprised, but not surprised that you start from a mole balance. And you
I
put
just
still.
have a quick
Go ahead.
question. So where does the 0.3 come from in the LN?
Log of 0.7, log of CA is 0.3 of CA naught, because it's a 70% conversion, right?
Oh.
Yeah. So CA is 0.3 of CA naught. So you can basically solve for this quantity. So that's how you begin. So that kind of reminds you of some of the problems we did with the Dem-Kohler number, and some of these. So it's the same idea. Now what the question is asking is, now that if the Tilly modulus is very small, so it's equal to 1 mostly. So if the reaction is done at 60 degrees, what's the new conversion. So that's something that you may be able to just actually do without having it been introduced to the effectiveness factor at all. Right. So what you can do is like, so if the Tilly modulus is small, so what that means that this is pretty much equal to 1, right? So now what you can do, you can make a, what's the best way to say it? You can take the ratio of the k's. So if you know what I mean by that is, you can say at 60 degrees, k at 60, I'll call it k prime, I guess that's what it's called, and k prime at 50, right? So that's basically, you can take k prime 60 divided by k prime 50, right? And that's equal to, of course, we know this, right? E to the minus 20,000 calorie per mole K, 1 time divided by 987 times the temperature, which is in this case 333, right? This is 60. So this is your, then you have same, except that now your temperature is at 50. So you have this. This is essentially, because eta is equal to 1, this is essentially equal to k prime. Well, I think I did it a little bit backwards, but it's actually the same as saying eta k prime w over v at 60 divided by, that's at 60 degrees C, divided by that k prime w over v at 50 degrees C. So normally that's where you start, right? You start here, but I did it backwards accidentally. So you start here, and then you say that, well, eta is equal to 1 in both cases, and everything else cancels out. So that's how you go from here to there. Does that make sense? Because eta is equal to 1 because the Tilly modulus is small. So then you can calculate using this. You can essentially calculate the new conversion. So let's see. So if you calculate
Dr. Nard,
this,
I'm kind of confused on what you did on the last 2 parts. Like I understand that you have the K equal to the A naught E, but how did you get the part that's in red?
so this is this. So what I'm trying to say, like I said, I did it backwards accidentally. So one thing you need to realize is you need to calculate a new K, right? You need to calculate a new K prime because the temperature has changed, right? Does that make sense?
Yeah.
So to calculate a new K prime because the temperature has changed, you do K prime at 60 over K prime at 50. Correct? Because remember, we did this thing. Yeah, so that's right. Okay. Now, you don't know K prime at 50. You don't know K prime at 50, but you know NK prime W over V at 50. So you take the ratio of NK prime W over V at 60 with NK prime W over V at 50.
Okay, so then the NW and V all just cancel out.
They cancel out because at very small Tilly modulus, the effectiveness factor is equal to 1. So you get, yeah. So that's what I mean. I actually did it backwards. I meant to start from the red part and then go back. And then go, yeah. That's what I meant to do.
Okay, thank you.
Yeah, didn't do that actually, unfortunately. But so if you can calculate this number, right? So this is 1.2, right? This number is 1.2. well, let me rephrase this. So yeah, so you can calculate this ratio right here. This ratio is just numbers, is equal to 2.55. So this ratio is equal to 2.55. So K prime at 60 over K prime at 50 is equal to 2.55. Okay, so from there, what you end up doing is if you go back to the mole balance, right? So you realize quickly that NK prime W over V at 60 is equal to 2.55 of NK prime W over V at 50. Right, that's from this. So that means if you go back to the mole balance, suddenly you have log of CA over CA naught, which is now your new unknown, is minus 1.2 times 2.55. And that means your CA over CA naught is equal to 0.05. So that means your conversion is 95%. Right, so it's just substitutions. So you know your K is going to go up, right? Because the temperature went up by 10 degrees. And that's the factor by which it went up. And you obtain that from doing this calculation.
So I'm just a little bit confused still on like how were you able to equate K to the effectiveness? I mean, to like what's in the red? Yeah. How
Yeah,
were you able-
so where we start is we have a relationship at 50 degrees.
right.
So what we know is that we need to find K prime at 60,
Right.
right? But we have this relationship for K prime that includes K prime at 50. So we can take that ratio and ask ourselves, what is it equal to? So if let's say you start from that ratio, you say, okay, what is it actually equal to? Now, since effectiveness factors are equal to 1 in both cases, this ratio simplifies to this.
Oh.
Yeah. Because
Right.
effectiveness factors are 1. You'll see in part B that it's not the same anymore. You'll have to do something else. But yeah, so effectiveness factors are 1, and W and V are the same, so these cancel, and the effectiveness factors cancel. You just left with this. So then you can basically calculate what that ratio is. And you can plug it in your mole balance, essentially, because you know that this ratio means that your reaction is going to go up by a factor of 2.55. The reaction, that relationship at 60 degrees is going to be 2.55 higher.
Okay, so then you go back in and you re-expand it.
You put it back in, yes.
Oh, that makes sense.
Yeah.
Thank you.
Mm-hmm. So that's a pretty easy part, actually. Part B is a bit more difficult. So I cannot say exactly what's going to be in the exam, but for example, the exam could ask you something like, well, is this reaction internal diffusion limited or internal transport limited based on data, right? It could ask you something like that. So that way you would know, because you all know at this point how to calculate the Tilly modulus for different reaction orders. And you know, you have a spherical catalyst, so you all know how to approach that that kind of problem. So that shouldn't be too bad. So anyway, so this is the first part here. So we can look at the second part, where now the Tilly modulus is very large. So this is a little bit more complicated. So if the Tilly modulus is very large, so part B, and don't get, we'll try to do it as best as we can, so that you can get confused. So if the Tilly modulus is large, the effectiveness factor is equal to 1 over the Tilly modulus. So that we know that's true. So what that means is the effectiveness factor at 60 degrees over 50 degrees is equal to the Tilly modulus at 50 degrees over the Tilly modulus at 60 degrees. So you can see how it's flipped, right? Yeah, so you can see how it's flipped.
Is that because it's like 1 over
Yeah,
50
because
over
it's
1 over 50?
exactly. So that's one thing you need to keep in mind. So you have to keep that in mind. Okay. So it could also be 3 over. So in some places, this is first order. So the real number is actually 3 over Tilly modulus, but it doesn't matter because the 3's are going to cancel. So you can say it's 1 over, it's fine. It's going to be the same. So that's one thing we know. And the other thing we know is that the Tilly modulus for first order reaction is equal to R K. In this case, I guess it's the K. Well, it's fine. We can take K that times. Well, let's write it differently. We'll just do KV. So that way, you guys can see something you've seen before over diffusivity, effective diffusivity. So that's the Tilly modulus for first order irreversible. Reaction. So what this means is that at 50 over Tilly at 60 is the square root of K at 50 over K at 60, right? That's what this is equal to, and these are K primes. Remember that KV here is K prime times density, but that's okay, densities are the same. So this is what you have. This is all the relationships you have. So first, we know that when the Tilly modulus is large, the effectiveness factor is 1 over that Tilly modulus. So that if you do the ratio, it flips the Tilly modulus ratio. So this is the Tilly modulus equation. So if you do that of 50 over 60, you get square root of K prime at 50 over square root of K prime at 60. And remember that this is still equal to, don't forget that. Yeah, this is that relationship that we need. Remember in the previous example, effectiveness factor was equal to 1, so we didn't really care to do that at all. We didn't care to know how it impacts the reaction rate constant, but now we do. So yeah, so then if we look at the ratio again, at 60 divided by if you look at this again, so N, I'll call it eta 60 over eta 50 is the square root of k at 50 over k prime at 60, right? And then that is times k prime at 60 over k prime at 50, because this is the k prime over k prime. So if you multiply these through, it just then equal to, I think it's ends up being, yeah, yeah, keep track of the subscripts. So okay. I apologize for my handwriting, because when I try to put my computer in template mode, it turns off. It is broken. So I'm writing vertically, and that's not ideal.
Why are you able to just multiply like that?
Well, you divide,
Why?
so so basically k to the k50, this is to the 1/2, k to the power of 1, so it becomes k to the power of minus 1/2, right?
Yeah,
k to the power of
I
1/2.
get
Yeah.
that, but like why? Because like you have the Tilly modules on the left, right, of 60 over, like isn't that like a substitution on the left side of the equation?
Say that again. I'm a little bit confused.
Like the left side where it says like efficiency times k prime times w over.
Yeah, this one, right?
Yeah.
Yeah.
Is it that, like, did you just write
So
that, or?
let me expand this so that I can. I'm gonna put one more step so you can see what's happening. Okay, I'm gonna put one more step. So this is eta 60 over eta 50, right? Times k prime 60 over k prime 50. And then we assume that the W and V's are they cancel out, right?
So I guess my question is like that whole left side is equal to that whole right side, or is it like you manipulated it by multiplying by k60 and times k50?
No, the whole left side here, right? So at right here up the top, we calculated what eta 60 over eta 50 is equal to. Now, if we go to the ratio over here, this 60 is just an identifier, nothing to do with anything, okay? So it's just saying that if you take the ratio of these two, what is it equal to? It's essentially equal to the ratio of one times the ratio of the other, right?
Yeah, what is inside the parentheses equal?
So this one you mean?
Yes.
I'm slightly confused about what is it equal to. I'm not sure, because, for example, this bottom one is equal to 1.2, but we don't need to put the numbers yet.
Okay, I'm like really confused, but just keep going and maybe I'll get it.
Okay, so since you're confused, let's see if we can explain this better. So the idea is the way that we go about doing it is by taking a ratio of the two quantities. And these quantities are nkw over v. So that's the idea. Another way you could do this problem, which could be more straightforward to you, is to do substitutions. But that's just a little bit more messy, because you still have two unknowns in two equations. Okay. For example, one unknown is the effectiveness factor, the other one is k prime. So you could do substitutions, express one in terms of the other, and that would be fine. But it would just be it will be a bit messier, which we're not doing now. So we take the approach of taking the ratio of the two quantities. And we have to evaluate what this ratio is equal to. So in the first part, we evaluate that ratio, the one thing that was happening in the first part is that the effectiveness factors are equal to 1. So you can cancel those out. And W's are also equal and V's are equal. So this ratio is the same as K prime over K prime at 60 over 50. So that's that. Now, if we go to the second part where the effectiveness factors cannot be, they're not equal because effectiveness fact is not equal to 1. It's 1 over Tilly modulus. So you have to calculate what this eta 60 over eta 50 is equal to. Okay, so then we do this little manipulation. Eta 60 over eta 50 is equal to Tilly modulus 50 over 60, which then is equal to K prime 50 over 60 square root of from this relationship. You guys still with me there?
Yeah.
Okay, now we go back to that ratio because this is the same ratio this is the same ratio. We go back to it and we tell ourselves, okay, nk prime w over v at 60 divided by nk prime w over v at 50. And I put this next step, which is the same as saying eta at 60 over eta at 50 times k prime at 60 over k prime at 50. We cancel out the w and the v's. And that's equal to this quantity, which is that. Plug that in times this. So it then becomes equal to this.
Oh, so from the left side to the left box to the right box, all you're doing is canceling out the W and the V's?
Yes.
Okay.
I just
That
added
makes-
that for clarification to make it
that makes
cleaner.
sense.
And then you just replace them. So now you see that instead of that relationship being k prime at 60 over k prime at 50, it's actually the square root of k prime at 60 over k prime at 50. And you can do the same calculation here, which is essentially the square root of 2.55, right? So this is basically equals to the square root of 2.55. And that's 1.6. And now we go back to the mole balance. So we go back to the mole balance. So your log of Ca over Ca naught is essentially equal to minus 1.2 times 1.6. And that's minus 1.92. And that means Ca over Ca naught here is 0.15. So that's 85% conversion. Now you should already sort of think that would be the case. So if you increase your internal transport effects, your conversion at 60 degrees goes down.
One of the questions I have is like, what was the whole point of like doing some algebra just to flip k prime 50 over k prime 60 to k prime 60 over k prime 50? Could you not have just done the inverse to begin with? Like, what were you trying to show with that?
Are you talking in here?
Yeah, like the second equation where you did, yeah, like right there, to get to k prime 60 over k prime 50. If we already knew from the beginning that that n6 or eta 60 over eta 50 equals k prime 50 over k prime 60 square root.
But keep track of the subscripts. So you see, oh, sorry, let me keep track of the subscripts. You see this? This is your eta ratio.
Yeah.
This
So it
is your
ended up
case.
creating a flip, right? And then what did you say the next thing was?
This is your k primes, which are in the equation, right?
Yeah.
Okay, so you can see how this went, it flips it from, so basically if you multiply through the K prime 50 goes to the denominator now.
Yeah, yeah, I understand that, like how you got to that. But yeah, like what was the point of ending up with that when, like, could you not have used the first one to begin with and just do the inverse? Or
why would you want to do the inverse? So the question is, yes, it gives you the same answer, but why, how you do justify it, inverting it,
okay,
right?
I see what you mean.
Yeah, like how do you justify inverting it? So yeah,
Got
it
it.
just happens to look inverted in the end, but it doesn't necessarily mean that it would invert every time, or it would be that the same every time. Yeah, that's more, this problem is more an advanced move. I wanted to do it so that, knowing that the exam as written doesn't have a problem like this, okay? But I wanted to go over it so that problems that involve, so let me be frank here. If you have to solve a CSTR problem with an internal effectiveness factor, you cannot solve it easily using by hand. You have to use Excel, for example. If the same problem is given to you to, let's say, solve for the fractional conversion, but with a PFR, once again, you have to use some like Python or some other differential equation solver, because the effectiveness factor can also often include your fractional conversion. First order, it does not, but second order, it does. So the problems of this flavor allow you to solve for these things without going through the pain, without having to go and solve differential equations and very complicated algebraic forms. However, it forces you to understand these equations. The notes are the solutions of the, so yes, Melissa. Yeah, everything's going to be posted. The notes are the solutions, so they'll be posted. So yeah, so that's essentially, I think these are the two parts that I gave as the homework, as the exam last spring. So I think part C, part C, it deals with external mass transfer limitations. So there's no point to really look at that. We can actually solve part D if you like. Let me see.
Dr. Denard, this could just be my brain not working, but the math from the stuff that's in blue, how did you get to the final thing that's square rooted?
This one?
Yeah.
I mean there?
Yeah.
Yeah, so k50, square root of k50 times k to the minus 50. K50 to the minus 1.
Oh, okay, I see.
Yeah, that's how it, yeah.
Yep. Thank you.
Yeah, so part D, you see, this would be something that is actually solvable. It's actually simpler if you think of it, because they're saying that the particle diameter is 6 times the original particle diameter. And I suppose here the diffusivity is the same, although they don't say it. But now let's say that the Tilly modulus is 0.5 and the catalyst is made with identical properties. So I guess they mean same diffusivity, effective diffusion coefficient. So that's good. And the particle diameter is 6 times larger. And to calculate the new conversion at 50 degrees. So this one is actually a little bit simpler because it tells you that at 50 degrees, the original conditions, so the very conditions in first part, that the Tilly modulus is 0.5. So now knowing the Tilly modulus of 0.5 and knowing conversion and temperature, you can calculate your effectiveness factor at a Tilly modulus of 0.5. Right, so what that means is if we do part D, so we can skip part C because it doesn't really pertain to what we're doing. If we look at part D, so at 50 degrees, the Tilly modulus is equal to 0.5. So the effectiveness factor is, I think, 3 over Tilly modulus times 1 over hyperbolic tangent of the Tilly modulus minus 1 over Tilly modulus. This is another first order reaction effectiveness factor equation. So then you can calculate that to be 0.98. So that's what the effectiveness factor is equal to. Now, if you, this is original condition. Okay, so original condition is 0.98. Now, if you increase the diameter of your particle 6 times, so the new Tilly modulus is essentially 6 times the old Tilly modulus, because the Tilly modulus is R times KV over D effectiveness factor, a diffusion coefficient. So it's just 6 times that. So the new Tilly modulus is equal to 3. Okay. So if it's equal to 3, then your effectiveness factor now is equal to 0.67 just by plugging everything in. Okay, so then what you can do is now go back to the mole balance again. If you go back to the mole balance, you have the log of Ca over Ca naught is equal to minus 1.2. And then the way you get your new conversion is by multiplying by the ratio of the effectiveness factors now, right? Because that's how you basically would get your new conversion. And that's equal to that. And then that gives you a Ca over Ca naught of 0.44. So this is basically taking the ratio. This is basically doing the mole balance at 2 different effectiveness factors. Because if you do the mole balance at 2 different effectiveness factors, you're gonna end up with having to just take the ratios of them. That's what's gonna happen. Because everything else is constant on the right-hand side, except for the effectiveness factor being different. Because it's the same temperature, so your Ks are constant, remember? So your Ks are constant, everything else is constant except for the eta. So it says basically, if you take the ratio of the etas, you would get, you know that you would get a lower conversion because you increase your radius of your particle. And you know by increasing the radius that your Tilly modulus went up. So that means you know that your conversion is going to go down. So you know you can just multiply your log of C over Ca naught by that ratio by which it's going to go down, because it's linearly going to go down in this way. So yeah, you could find a different way to do it. And I think the way, you know, different people's brains work, you can do a few different loops to find out how it works. But this basically is a simple way to look at it.
I'm a little confused on how you calculate conversion with just the ratio of
Well,
CA.
this, yeah, so that means if, let's say Ca naught is 1, Ca is 0.44.
Oh, so you can just test different. Oh, I see.
Yeah, but originally, like even before doing the problem, you would know that the conversion is gonna be, so now XA is gonna be 0.56. Even before doing the problem, you would know that the conversion should be lower because you increased your diameter by a factor of 6. So if by doing that, you know that you're increasing your internal transport effect because you have a much larger diameter. So you would know that.
Okay, I see.
Yeah, the problem, for example, in the exam, it could ask you, and I think, well, maybe not, but the exam you could be asked, you don't have to calculate, you could be asked to comment on what would happen, right? Instead of having to do the calculation. And you would basically have to think about what would happen if you have a different catalyst or different diffusivity, if certain things change. And you can try to explain what would happen to, say, selectivity or yield or conversion or things like that.
Okay.
But keeping in mind, guys, like it's all revolving around a few equations. It's like, you have this guy, this one. It's all evolving around these equations and mole balances. So
Wait,
it's not,
you said that XA is 0.56, but isn't, oh, okay, so it'd be 1 minus the 0.4.
yes, it's 1 minus the 0.44.
Did you skip part C?
I did, because the answer to part C involves external limitations, which we did not go over. Yeah, we went to part D. So yeah, last spring we went through all of it. That was the one. That was actually that was the hard problem on the exam last spring. So I wanted to go over that just to tell you this is not what you're gonna see. You'll see something not related, but not like that. This involves a few algebraic gymnastics, I think, but it's not so bad. Let me see if I can find another good problem that we can work through. Let me find a good one. See, I'm very biased because I know exactly what's on the exam. So, and I know that if I solve a problem that is not on there, I mean, it's not a waste of time, but it's also, it doesn't, yeah, it'll put me in a bad position. Okay, well, okay, let's look at an interstage cooling one. So let me let's look at an interstage cooling problem. See if I can, is it gonna work if I do the pasting of this here? No. Give me a second. Oh, that's not good. That's not what I meant to do. Let me try again. Okay, let me try one more time to copy and paste this on the page. There we go. Okay, and then I'm going to also put the graph, because this problem is actually not very difficult. It does. So, okay, so I'll give you guys another few minutes to look at it and read it, and then we'll do the solution. Okay, let's give it a try. Yeah, let's give it a good try here. Let me see. Yep, so you're given an inlet temperature of about 320. Is that am I correct here? The temperature that it's coming in at is 350. Then you're reaching about 99.9% equilibrium, so you can say that's close to 100. So that's good. Now this is adiabatic. So what you need to know first is what your adiabatic temperature is in the reactor, and that's just looking at the slope. This is basically looking at, this is not so bad because I think we looked at something like this in class. This is looking at your outlet temperature. I don't have the full solution in front of me, so I apologize. So you have your outlet temperature is T naught plus minus delta H of reaction. And here I think we're assuming that delta Cp is 0. Yes, because the Cpa all through Cpd is equal to the same. So delta Cp is equal to 0. So there is no change there's no change of delta H of reaction with respect to temperature. And that's equal to Fi naught Cpi times Xa. And that Xa is 99% of equilibrium. So that's the line we need to, well, we need to solve for Xa. So the first thing we can rearrange this. So I'm gonna put this in terms of X equilibrium because it's 99.9% equilibrium. So we can assume that, okay, it's gonna reach the equilibrium line. That's what we're saying. So we can solve for the equilibrium XEB. So, and that's equal to, so I'm just gonna go ahead and put in Fa naught Cpa times T minus T naught plus Fb naught Cpb times T minus T naught divided by delta H of reaction minus delta H of reaction times Fa naught. And that's equal to your equilibrium conversion. So that gives you a straight line essentially. And then you can draw that line. You can get that slope and draw that line. So let me see what it's equal to if I put it on all the numbers. Let's see. Is Fa naught equal to Fb naught? Are they coming at the same? Are they coming in at the same? Yes. So they're coming at the same. So you can essentially delete. Yeah, that's really good. So then you can have, it will simplify to it just simplifies to this. Yeah, that's good. And that number is equal to 2 times 10 to the minus 3 times T minus T naught. So that's your X equilibrium.
Dr. Denard, where does it say Fb naught equals to Fa naught?
Yeah, I'm trying to see if that's the case. I would love it to be.
It says it's equimolar, I think.
It does it say it's equimolar?
Oh yeah, in the
second line in the second paragraph.
Aha, equimolar A and B. Yes, so they're equal.
Thank you.
Yeah, I was also not looking. So yes, so they're equal. So you can simplify everything. So you can draw this line. And so the question is, what is this line gonna draw like? Now, you can double check for me seriously, but if we, at least from some solution I found, the so it's 2 to 10 to the minus 30 minus t naught. So let's see if we. So what's the exit? Enters at 350. So we can find out. Yeah, we can make that line. So it enters at 350. So you can double check for me because I don't have the solution in front of me, unfortunately. I just started solving it like 20 minutes before class. So let's see, that line is gonna be, let's assume, hopefully I'm right. Let's assume it goes, let's say to there. I'm not sure. I'm not 100% sure. But let's assume it goes through there. Unless somebody can calculate it really quickly, what the slope is and how you, and to draw a line that reach the equilibrium.
Isn't the y-intercept like 0.7? It's just 350 times 0.002.
Well, minus 0.7.
Yeah, minus 0.7.
Yeah, minus 0.7. Yeah, but yeah, that's true. It's minus, so it goes. So I guess it's not. It goes up a little steeper, right? Because if you go minus 0.7, so I guess it goes up a little steeper. But that's not right. That doesn't look
It
right.
looks like it goes up by 0.7 every 50. No. All right.
That's not right.
Something seems off.
That seems off. Okay, so I'd have to look at it again to make sure that I'm not messing something up like really badly. Maybe with the, yeah, I need to make sure. But let's see, what's the idea there? Okay, so for the sake of demonstration, okay, for the sake of demonstration, we don't know what the actual slope is gonna be. At least, there might be an error in this problem from point of view of what the slope is and how we go up the slope. Okay, for the sake of demonstration, let's assume that the first leaves at 0.4. Okay, so that might not be correct, but every time we cool it down back to 400. So yeah, so according to this problem, if a single reactor would be at 0.4, if assuming that this is correct, right?
So that's just like after you draw the line of this, like the slope of the line, and like it's wherever it touches that equilibrium line.
Exactly, that's where it's gonna stop.
And then I also was wondering like the difference between like, it says like achieving a 99.9% of the equilibrium conversion versus like a 30%. Like I'm just like confused on what that information tells us.
Oh.
Or like also when you say like the feed enters the first reactor, you have enough catalyst so that each reactor can achieve 99.9%. Like, is that supposed to tell us something?
Yes. So this line that you see here is the equilibrium conversion line, and it's a temperature dependence.
Right.
So then reaching 99.9% of that is basically 99% of whatever that point of contact is. So for the sake of argument, we assume that it reaches it, right? So it's 99.9% for the sake of argument. We assume it reaches it. So let me check this That's a weird problem telling us what the conversion is out of the reactor. So CPA, that's 100, and that's 100. So the slope is not 2 times, well, no, it's 2, yeah, it's 2 times 10 to the minus 3. So the slope is correct, and it's T minus T naught. Yeah, that's correct. Yeah, that equation is correct. Okay, good. At least that's something I did right. Then the question is, what's the first reactor gonna operate at, really? And one of you told me that it was gonna be that this slope is gonna be something much higher. I'm trying to think if that's the case. So 2 times 10 to the minus 3.
Every 50, it should go up 0.1 on the X equilibrium. I'm a little, I was a little bit off on the slope before because I didn't realize that the temperature scale started at 300. So like at a temperature of 0, you're at negative 0.7.
So it goes by 0.1 every time.
Yeah, 0.1 every 50.
Aha. Oh, so it looks like I did it right the first time. About, right? So
Close.
0.1. Well, I was off, but okay, I get close. Good. Okay, good. That's good. Can I do a line? Oh, would you look at that? Sweet. Okay, so this is your first conversion. Sorry, guys, my bad. So we'll try to do a couple of straight lines there. Really cool. Yeah, so about 0.3, maybe 0.34, something like that. Really cool. All right. Now, if you keep going up, because you have 3 reactors, this is your first one. So if you keep doing the same, but every time the reactor goes, the cooling goes back down to 400. So if you now start from 400 and you go in the same, oh no, we're talking about straight lines these days. We don't mess around. All right. Let's say we're gonna do a parallel line, more or less. Yeah, that's good. So if we do a
Don't we
parallel
cool
line,
to, sorry, don't we cool to 370 first?
370. Yeah, we go to 370. I was thinking we go to 400. So we go back to 370. For the sake of anything we're gonna do, and we're gonna pick numbers that we actually have that are in the 50 that are in the 50s or the hundreds instead of doing this, because that looks a little messy. So then you can look at the second conversion right here. So if we go back again down to 370, you can go up again, parallel line, and that gives you your last conversion out of the
Would
third.
it be 400 for the after the second cooler?
Ah, you see? That's why I have you guys. That's really nice. So
Also, I'm really confused. Like, what was the
Mhm.
point of the 99.9% number?
So it says that there is enough catalyst to achieve 99.9% of equilibrium. What this means is that when it reaches this point, right? That point there, it reaches 99.9% of that point. Okay, let me give you an example that is different. So let's finish this one. Let's finish this little climb here. So we're gonna go back to 400 now. So we have a second conversion out. So now we're gonna go up and now it's at 400. So we can go up here, out of second reactor, and then our last conversion is gonna be something like this. I meant to do a line. Something like this. Okay, so this is your last conversion. Now, your question is, what does it mean, the 99.9%? Okay, so I'll do an example here where we'll take a similar graph. Okay, this is equilibrium conversion temperature. So let's say instead of 99.9%, it was 90% of the equilibrium conversion. Right, let's say that's what you were reaching at that temperature. So if you're reaching 90% of the equilibrium conversion, you can calculate the equilibrium conversion at that temperature, right? Because you have a curve, correct? So let's say this is the temperature that you exit at. This is the temperature that you are. You can calculate the equilibrium conversion at that temperature because it's the curve. Now, what happens is that if you only achieve 90% of it, you are here. Or you're not there. The equilibrium conversion, you're only at 90% of it. So your curve, instead of going here, as we did earlier, say for example, would actually go there. You see you see what I mean? Are you still confused?
No, I see it now.
Okay, so by 99.9%, it's just making it easier for you to just touch the curve. Because if it's 90%, you're not touching the curve and it becomes a little bit more complicated to calculate.
I have a question.
Mm-hmm.
So, all right, this may sound a little stupid, but bear with me here. We have a graph that plots the equilibrium conversion with respect to temperature.
Yeah.
Right? We're given a temperature. What keeps us from simply, matching the temperature we're given to the point on the curve? What does that actually tell us, and why is that wrong?
Can you say that last sentence again? Matching?
Okay, so for example, we're given a feed of 350 Kelvin.
Mm-hmm.
Right? Why not go to the 350 Kelvin, marker on the temperature curve, or on the temperature line, go all the way up to the top of the curve?
Oh,
say
like a
99.9.
a straight line up, you mean vertical?
Yeah, what does that curve actually tell us? Right?
If
Why
the
can't we?
if the curve is vertical, what it means is that your the flow rate that you're operating is very, very high, right? That's your slope rate, right? You have a very high molar flow rate.
I guess what I'm asking more is, how is that curve plotted? Like, what does it actually tell us?
You mean the red?
How did we get a value for 350 is equal to 0.99 and 400 is equal to like 0.9, whatever that is, 6, and 500 is equal to 0.5? The big curve that goes kind of like starting at 1 and goes all the way down to 0.
Oh, that curve?
How do you get that curve? How do you plot that curve?
Yeah. Good question. Yeah, good question. That curve is from the first part of the problem, which we did, which is basically given to you. That curve is the equilibrium. So let's see if we can write it. Let's try that right there. K equilibrium is concentration of C times D over AB, right? So now if you go into stoichiometry, this is Ca naught XA times Ca naught XA over Ca naught 1 minus XA times 1 minus xa squared, right?
Okay.
Okay. Now you can, and then you also have, so this gives you xa squared over 1 minus xa squared. Okay. Then you
Okay.
also have K equilibrium C is equal to K equilibrium at a reference temperature times exponential to the delta H of reaction over R times 1 over T minus 1 over T reference.
Okay.
So now you see every time you change the temperature, your equilibrium conversion changes, then your X changes.
Okay. So I guess my question then is, since we are given a temperature, why can't we read a point off of that line directly?
Which is what we did.
No, we drew we drew a
Yeah.
slope.
So
Why do we need to draw a slope? Why can't we just go straight up?
yes, because you can't. The reason you cannot do that is because to be able to do that, your slope would have to be equal to what? Infinity? Like a straight line up. What is that slope? Because you'd have to basically say, oh, you go straight up, right?
But to get that point originally, right? To get that straight up point originally, you plugged in a temperature and got an X equilibrium, right?
Mm-hmm.
So why aren't we able to just plug in a temperature and get an X equilibrium? What changed?
So this value here, this particular thing has nothing to do with your reactor, right?
Okay.
It's nothing to do with your reactor. You don't have flow rates. You don't have any. You don't have molar flow rates. You don't have coolant. You don't have CP. You don't have anything. So this is something you can calculate based on the reaction, not the reactor. So this curve is just a thermodynamic curve, right? It's a thermodynamic curve that's nothing to do with kinetics.
Okay.
So your question is, couldn't you're asking me if I say that you're operating at 350, couldn't you say that the equilibrium conversion is this? That your conversion is this? That's what you're asking.
Yeah.
Yeah.
Yes, yeah.
Well, the problem for you to operate at this, you'd have to have a reactor where the slope is essentially a straight vertical line.
You said that the curve itself comes from the reaction. It's thermodynamic space.
Yes, the curves from
Right.
the reaction. It's nothing to do with your operating conditions.
So between the reactor and the reaction, we connect them through that equation, I guess.
So this equation here, you can
No,
see
we
that.
connect them through the equation that gives us the slope.
Yeah, so this equation that gives us this thing,
Yeah.
is your operating conditions of your reactor.
Okay.
Yeah, so you could not go straight up. You'd have to have an infinite slope to go straight
So you
vertical.
really
And where are you finding the
couldn't
slope from?
reach-
Say that again for one. I think
ahead,
Where are you
Josh.
finding the slope from?
the slope is from here. This is your adiabatic energy balance, where if you solve for the conversion instead of temperature, so you can say that you find this equation that tells you what the line looks like.
How do you know like conversion and then the X equilibrium is the same?
The reason I put that as the same is because we actually let me not do that. That's not a good idea. Okay. Let's just call it XA, because I think I may have misled you by doing this. That's not a good idea. Okay. Let's just say that's what it is, because the problem tells you that this XA is 99.9% of the equilibrium. That's what the problem says.
So like if you're at like on the first reactor, it's like 0.32 or whatever.
Yes,
If the X equilibrium is 0.32, then 99.9% of 0.32 is the conversion.
is the conversion.
So then XA would be like 0.3, like
0.31.
0, 1, or 100, like 999 or something like that.
Yeah, well, 0.31 something something.
Okay.
Yeah. Yeah,
But since it's so close, is that why you can just assume
that's right.
like XA is equal to XEQ, which is why that number, like when you say it's like 99.9%, that's like so that you can just like when you estimate it, you can just say it's the same thing.
Exactly. That's
Okay.
why it's said
That
that
makes
way, so
sense.
that you can make that assumption, because otherwise you'll have to do a couple of changes. But that other question that in terms of it, the question about thermodynamics versus kinetics, is that answered, or do we still need to cover that?
Could you just do it one more time?
So this line, this curved line, is generated from a thermodynamic relationship of equilibrium, which is this. So what it says is that for an exothermic reaction, as you increase temperature, your equilibrium conversion goes down. That's a known thermodynamic thing, and you can plot it using these two equations. This one, well, you pick a temperature, you find an equilibrium, plug that in, and you find an X. So then you can plot temperature, you can X versus temperature, equilibrium X. So you can plot this thing. It's nothing to do with your reactor. It's just a thermodynamic relationship. Now, when you operate your reactor, you can only reach that equilibrium. When you reach it, the conversion does not go any further. That red slope is the operating condition of your reactor adiabatically. So now if you have an energy balance for an adiabatic reactor, looks like this, and you want to calculate X as a function of T, you can solve for X as a function of T. So you basically make that little algebraic change, right? You can just solve for that. And that gives you a line, which is XA. It gives you this line. So as you change temperature, you'll get a different XA. And you're gonna go along the slope. But the problem says that every reactor can reach 99.9% of the equilibrium. So if you make that line, when you reach 99.9% of equilibrium, you stop. And that's where your conversion is. And then, well, it says, okay, now you can stage where you can cool it down again. And then you go to a second reactor and you do it again. But you actually are going at the same exact slope because your flow rates are not changing. These are not changing. They're FB not. Because the reason why they're not changing is because the total flow rate is going to be the same. The total molar flow rate is going to be the same because you have an isomerization reaction that goes back and forth. So if you keep adding those, it's still going to be equal to the total inlet flow rate because of stoichiometry, right? Because of stoichiometry, the molar flow rates are going to be the same. Now, this is not liquid, this is not gas phase, right? If it's gas phase, then you have some changes in volumetric flow rate that can change some things, but this is liquid phase, I think. Yeah, I think it is. It doesn't say, but I think the assumption is that it is. So yeah, so that's why the slope is there. You can reach the equilibrium, and once you reach it, it stops. You can cool down and then try again, reach equilibrium. It reaches a higher equilibrium, and then keep doing it until you reach a point where essentially you can't go any further. Because you could go infinitely, right? You could keep going and going and going and going until you reach a point where you basically can't go any further.
So if we wanted to reach, like, let's say past 90-degree or 90% conversion, would we have to cool down the reactor or like the feed past 300 degrees Celsius?
Yeah, you could do that.
Or I mean 300 Kelvin and then hit it?
Yeah, you could do that. You could cool all the way there and then see whether or not, if you make a straight line that's parallel, Yeah, you'd hit it. Yeah, you'd be going up here.
Okay, so you can cool past the first point. It doesn't matter as long as
Oh
you're
yeah,
cooling
you
past
can.
there.
But here's the problem, right? Now we didn't talk about that, but there's a practical consideration. The lower the temperature that you cool your species to, the larger the reactor you're gonna need to get the reaction to go, right? Because it's
Yeah.
exothermic and Ks are depending on temperature. So yeah, you can do it, but is it gonna be practical from the point of how much, what reactor size or how much catalyst you need? For example, if you're operating at at exothermic reaction at 300 Kelvin, and you only need to convert from 0.7 to 0.9, for example, it might not be practical because you might find out the reactor you need is as big as the first one or larger than the first one. You know what I mean?
Yeah.
Yeah,
'Cause,
there's a
like, there's not enough
consideration.
heat to keep the
Exactly,
reaction
not enough heat to
running
get the
fast.
reaction going. So there is a
Yeah.
consideration from the practical side. But in theory, yes, you could do anything. You could do all of it. Practically, it's not that straightforward.
And then also, like, let's say the reaction goes past like a certain temperature range. Like, let's say the second reactor went past 500 degrees Kelvin, right?
Well, it could
Does the
not.
conversion go down or?
No,
oh,
no, it could not.
Okay.
Because the reason it could not is because there is a relationship between conversion and temperature. So the reaction could not go past this point.
Okay.
It could not, because if you know what would happen if it tried, it reached equilibrium. So it cannot go any further.
Okay.
Because it reached equilibrium, it cannot go any further. Your temperature also cannot go any further because there's a relationship between the two given by your energy balance.
I see.
Yeah, that's why. So if X cannot move, T cannot move.
Mm-hmm.
Yeah.
Thanks.
Yeah, okay. So on the exam, you can expect a problem related to the first thing we talked about. It's a kind of similar approach because, as I mentioned before, it is very difficult to ask you to solve a problem where you have to use Excel on the exam, because when you introduce effectiveness factor in a CSTR or in a PFR design, it quickly becomes difficult to solve by hand. So on your exam, you can expect a problem that is very similar, or not very similar, but that goes in the same direction as what we solved. Basically telling you these are the conditions at a certain temperature or at a certain effectiveness factor or with a certain Tilly modulus. So you have three choices, right? And what would be the new conversion or the new Tilly modulus or the new effectiveness factor at a different condition? And you just have to relate them. One way you could do that is taking ratios of two quantities that you need to know, or by doing substitution. Say in the first problem, you could have calculated K prime as a function. So instead of doing this, you could have calculated K prime as a function of W, N, and V. You just flip everything to the right, right? You could do that and then replace that in this A naught E to the, you could do that, right? That would work. It would be the exact same approach. You just would take a ratio instead of doing a substitution as you would normally. Because I think that's what your brain would try to do, is to substitute. But you could take a ratio. It's the same idea. It's the same idea. So you can have there's gonna be a problem that relates like this. And there's gonna be a problem with an energy balance. So your take-home exam, which you should take seriously because it's a lot of points. It's not difficult. And tomorrow we'll talk about it if you have the time. and you want to stop by and check it out. But that won't be recorded, by the way. FYI. So, yeah, it won't be. But yeah, so if you, yeah, you should be able to do it. It is not difficult whatsoever. Now, the one caveat is on the exam, I said that it asks you to generate a G of T curve, a heat generation curve for your reaction. I tell you, if you're stuck and you cannot do it, you can ask me for my data, and I will give you my data so you can continue the problem. Okay. There is an 18-point deduction. I don't know if it's 18 or 15. There is a deduction from doing that. But you're free to ask if you feel that what you've done, either you're not comfortable with it or it gives you errors. That's the first thing. And the second thing, you should, if you can, and if you're comfortable with it, discuss with peers. Show your own work, but you can discuss it. You can say, okay, this is how I did it. And someone could say, this is how I did it too. Compare some of your results. That's fine. I cannot stop you from doing so. And I encourage you to do it so that it's about learning. Obviously, I hope someone doesn't just give you their data, which, I mean, at that point, no one can tell how it works. But I encourage you to do that. This is not something that I can control anyway. And tomorrow when we discuss, I'm not gonna tell you if you got it right or wrong, of course. I'm just gonna discuss approaches and failure modes. For example, if you use Solver, there may be places where where it fails, and I can discuss that, saying, okay, if we approach it that way with Solver, it may not actually work. And I found 2 failure places, and I assume that you may also run into them. Yeah, that's what I wanted to say there.
Dr. Denard,
Mm-hmm.
for the actual final on Thursday, how long are you, or how much time are you setting aside for that?
I'm still gonna give 2.5 hours, but the problems are gonna be, it should take you about an hour. I'm still gonna give the time. I'm not into giving you, speed up things. No, I'm still gonna give you the time. It says 2 hours block off. I'm gonna add a half an hour just to for you guys to upload your things and make sure you don't run into issues. So yeah, it's still the same, but it's gonna be 40 points, and you'll have yeah, good question, right? I have not finished Regrading Exam 2. I have not had time to finish it. I will. I can promise you that I will. Yeah, I've had a semester that's been pretty brutal. My lab just started, and for some reason I'm always in there because I'm teaching the students everything. So I'm in my lab from like 8 a.m. until I teach, and then I'm back in again. So it's a bit of a hassle, but I'm getting there. So yeah, we're gonna go through it. Don't worry. There's no promises broken there. We're gonna get it done. And you'll get your grades updated. There's a maximum of 7 points, I think, that could be awarded to most people. So you can take that into account in most cases. And the points are basically the people that gave an answer without explanation, and I realized that may have been because of time issues. And I'm just gonna give points for the right answer that wasn't explained. That's really the main crux of it. So, okay, I hope this helped, guys. I know it's a bit different maybe than what you have done with Alex, or maybe it's, but I wanted to only, here I covered things that could be on your exam. Now you can expect some first problem that looks like kind of like this. You can expect that, I can tell you for sure. The second one, maybe not, but I'm still debating. It's not for sure, but at least you've got one thing that you know to expect and to start thinking about, and how do you solve them. So that's all I have. I hope that it helped. If it didn't, I apologize. Might be too late now, but yeah. Any questions? It's 5 o'clock, but any other questions?
Yeah, I have a question for the people that are taking the exam on a different time or date.
Mhm.
At what point do we have to tell you by of like when we
Oh,
want to take it?
I think I already have the people that are doing it. I just need to email you back tonight to tell you this is the time, because the people that are already doing it, I know. I would love for you. Okay, let me say this. I should announce this if you're not here. I would love for you to send me a quick email literally right now and say this is the time, Thursday or tomorrow, which is Wednesday.
Yep.
Yeah, tomorrow or Friday. So seriously, I'm gonna post that right now, so to make sure, because I have scattered emails and I've written down some names, but I actually don't know if that's everybody.
Yeah, because I think I sent you an email, but like I didn't get a reply back.
Yeah, I didn't. I of course, yeah, I didn't reply. If let me on it. Is the recording stopped? Let me make sure that's